All right, so we're going to do 10.5 part 2. So we're going to come up with a way to find arc length and surface areas of revolution using polar coordinates. So we're going to follow the same thing we did for our derivatives. We're going to go back to what we talked about with parametric equations and just substitute our conversions for polar coordinates. So let's remember our arc length with parametric equations was S equals the integral from A to B of the square root of dx dt squared plus dy dt squared dt, where we're saying that x is some x of some function of t and y is some function of t. So those are parametric equations. So we're going to substitute for polar coordinates. We're going to substitute x equals r cosine theta, and r is a function of theta, so I'm going to say r of theta cosine theta, and y is r of theta sine theta. And then we're just going to substitute that into this expression. So what I want to do next is we're going to find our derivatives and substitute into this expression and come up with this integral expressed in polar coordinates. So let's find our derivatives. We're going to take dx d theta and dy d theta, square them, add them together, and take the square root. So it looks a little messy at first, but it comes out kind of nice. dx d theta. We did this when we talked about finding our slope. So dx d theta, what is going to be my expression for dx d theta? We're going to use the product rule. So we get minus, and I'm going to drop the theta with the r. We know that r is a function of theta. So we get minus r sine theta plus r prime cosine theta. And dy d theta, I'm just going to use the product rule again. We get r cosine theta plus r prime sine theta. And now we're going to square these. So dx d theta squared. And we get, what do we get? R squared sine squared theta. And I get a r prime squared cosine squared theta for the outside terms, and then the inside terms I get a minus r prime sine theta cosine theta. Are we good there? And dy d theta squared equals what I get a r squared So this looks kind of messy. Here I get an r squared cosine squared theta. Oh, this is looking okay. And for the outside, for the last term, I get a plus r prime squared, and this should be a squared, not a 2. I get an r squared, r prime squared sine squared theta. And then for my mixed term, I get a, let's see, do I get a, and this should be a, I missed a 2 here, didn't I? I get 2 of those. Do I get 2? Yeah. And here I get a plus 2 r prime sine theta cosine theta. And we're going to add these together now. We want to add those together. So I end up with these two terms cancel out, and I end up with an r squared sine squared theta and an r squared cosine squared theta and an r prime squared sine squared theta and r prime squared cosine squared theta. So what am I left with? I just get r squared plus r prime squared.
Oh, hey, that's
So we don't even end up with any sines and cosines. So our arc length in polar coordinates is s equals the integral, and we're going to go from alpha to beta for our angles of the square root of r squared plus r prime squared d theta. So that's our expression for arc length in polar coordinates. One thing that we have to be careful with when we're finding our arc length is that our curve is only traced once on the interval from alpha to beta, and we want to make sure that it's not intersecting itself somewhere in between that the limits of our integration. So questions on that? Looks pretty similar to the arc length integrals that we've been using before. And we can, just like we did in rectangular coordinates, we can think of this as ds, the arc length as ds, it's a little piece of arc length, and that'll come in handy later. So what I want to do next is find the perimeter of our favorite cardioid. Our favorite, we've used it a lot. The one we've been using is r equals 2 plus 2 cosine theta. And that's, do we need to see the graph of that one again? Yeah, let's look at the graph. All right, there's our cardioid. Grab a picture. Oops, I didn't want to do that. There we go. Okay. There's our cardioid. 2 plus 2 cosine theta. So we want to find the perimeter of this thing. And we decided before that this graph is traced once from 0 to 2 pi. So I'm going to just work with the top half. I'm going to integrate from 0 to pi and multiply by 2. So this is traced once on the interval 0 to 2 pi. If you weren't sure, you could plug it into your calculator and graph, or we could decide r equals 4 when theta equals 0, and r equals 4 again when theta equals 2 pi. So we're going to look at the top half. So we're going to say here is r. So that's part of what goes into our integrand, and we need r prime. So dr d theta. R prime is just going to be minus 2 sine theta. And r prime squared is 4 sine squared theta. And r squared, the other piece of our integrand there, is going to be, when I square this, I get 4 plus 8 cosine theta plus 4 cosine squared theta. So this kind of looks intimidating at first, but then I see this, and I think, okay, everything might be okay. So we're going to add these two together, r squared plus r prime squared. When I add these together, I get 4 plus 8 cosine theta, and I get 4 sine squared theta, cosine squared theta, so I just end up with a 4. So I can simplify, I can factor out an 8, I get 8 times 1 plus cosine theta. That doesn't look too bad. But we need to, now here's the tricky part. We have to take the square root of this, right? So our arc length, so this, we were feeling hopeful here, and now we're looking at this. 0 to pi of the square root of 8 times 1 plus cosine theta, d theta. Oh, this doesn't look great. But someone said Wolfram alpha, but there's a resource that's even closer at hand. If we look at the front of our book and say, what trig identity could we use? Lo and behold, there's one that says 1 plus cosine theta equals 2 cosine squared theta over 2. Oh, look at this. We have a cosine squared and we have a square root. How nice could that be? So now I'm going to substitute that into my integral. We didn't even have to ask Stephen Wolfram. 2 cosine squared theta over 2 d theta, and this just becomes the integral from 0 to pi. When I take the square root of this whole deal, I just end up with the absolute value of cosine theta over 2 d theta. Oh, I forgot 8, 16 for, to be 16, so I take the square root and I end up with 4, yes. Yeah, so this would be the top half. So we're still talking about the top half, but yes, we need to do that at the end. So we cosine theta over 2 on 0 to pi. Is cosine theta over 2 ever negative on the interval 0 to pi? No, it's positive on 0 to pi, so I can drop the absolute value. And I can just say that our arc length of the top half is 4 times 2 sine theta over 2. And we're evaluating that on 0 to pi. This comes out to be 8. So our total perimeter of the whole thing is 16 units. So after all that worry in there about our integral and how we do it, we end up with a nice number, 16. All right, questions on that process? If you needed some identity like this to evaluate an integral on the test, I would provide you that identity.
It's no fun.
That's no
Takes all the fun out of it.
right. And this one, that's not one this is not one that I remember. I would have to look for that one. You knew that one, right?
Yeah.
Okay. Okay, good. No questions? So next I just want to talk about how we're going to come up with a formula for, or an integral for, a surface of revolution. So if we're revolving a curve in polar coordinates about either the polar axis or about the pi over 2 axis, how are we going to express that integral? And again, we're going to go back to what we talked about for parametric equations. Okay, so area of a surface of revolution. So we're going to start with our surface area integral for polar coordinates, or in parametric equations. We said that our surface area was integral from A to B, and we said R, whatever our radius of revolution was, times the square root of dx dt squared plus dy dt squared dt. And we're saying R can be a function of t. So we express our radius of revolution in terms of our parameters. So our radius of revolution in parametric equations, usually if we're rotating about an axis, it's either going to be our x coordinate. If we're rotating about the y-axis, it's going to be the y if we're rotating about the x-axis. So we're going to do the same thing. We came up with an expression for this radical. That's our ds, that's our piece of arc length. And our r of t is either going to be, if we're revolving about an axis, it's either going to be our x or our y. So in polar coordinates, we'll write down both of our integrals. Oh, and I forgot something here. I forgot my 2 pi. We have our 2 pi for our circumference. So S is going to be 2 pi. The integral from alpha to beta of, and I'm going to say R, but we know that R is a function of theta. R sine theta times the integral of R squared plus r prime squared, d theta, and we would be rotating about which axis here? About the, and in polar coordinates we call the x-axis the polar axis. Polar axis is theta equals 0. So this is about the polar axis. And our second integral, our surface area of revolution is going to be 2 pi, the integral from alpha to beta of r cosine theta times our arc length. And this is going to be about theta equals pi over 2. I'll just write it in here, theta equals 0. Polar axis is theta equals 0. And again, we want to make sure that our graph is only traced once on our interval. So we don't want it crossing over itself and continuing on that interval. So just like we've done before, we're just extending this using our expressions for polar coordinates to come up with these arc lengths of revolution. So questions on how we came up with these. Now, as you can imagine, just looking at these, that a lot of times these integrals take a little bit of work to simplify, and some trig identities maybe to get it to a point where you can evaluate. But that's kind of part of the fun of this. Is doing that. I'm going to give you one hint. Often, if you have an equation, if you have an equation in the form r squared equals f of theta, so we have a lemniscate or something like that, it can be easier to, it can be helpful to use implicit differentiation to find dr d theta. So rather than taking the square root of both sides and then going that way, we use implicit differentiation. So for example, if we had, if I had r squared equals 4 sine theta, I would write, to find the derivative here, I would write 2r dr d theta equals 4 cosine theta. So dr d theta is 4 cosine theta divided by 2r, so we just get 2 cosine theta over r. And in our arc length integral, we need dr d theta squared. So dr d theta squared, if we're finding an arc length or a surface area, we would get 4 cosine squared theta over r squared. Over 4 sine theta. So we end up with cotangent theta, cosine theta. So that's a little easier. I think that's a little easier than taking the square root of both sides and then finding your derivative. So just a hint if you're dealing with something with an r squared. So questions on that? Okay, that's all I wanted to talk about today. I found, I have found a couple of other demonstrations to show you, and then I said maybe we try to, while we're working, I might try to search for something in polar coordinates that we could do a sketch of pumpkin on our calculators. Oops, that's a wrong page. So we're on page 731.
I need a mug. There's push one box.